Good afternoon, everyone, and welcome to Webinar Wednesday. We are excited to have over 700 registered attendees for today's webinar, which is eligible for 1 credit from the ACI. Let's get started today by giving one lucky attendee an ice blanket for answering this trivia question. What is the official state tree of California? Answer now using the questions feature on your dashboard. While you're answering, I want to invite everyone to join us for the MD Expo conference, which will bring HTM professionals from across the nation to Irvine, California for 3 days of learning, networking, and the latest advances in technology, products, and services. Registration is now open. You can receive complimentary admission by using a VIP pass, compliments of Conquest Imaging, which can be found in the Webinar Wednesday workbook. If you did not receive this workbook, you can download a copy now using the handout section of the webinar dashboard. Details for the MD Expo can be found online at mdexposhow.com. All right, and the winner of the ice blanket is Benjamin Covington. Congratulations. The correct answer was the redwood. Webinar Wednesday would like to thank our sponsor, Conquest Imaging. Conquest Imaging is the largest supplier of ultrasound parts, probes, transducers, probe transducer repair, training, service, and free 24/7 technical support. For more information, visit conquestimaging.com. Our presenter today is Jim Rickner, Training Director for Conquest Imaging. He has over 30 years of experience working on a variety of electronic equipment and is a renowned instructor and sought-out speaker in the ultrasound industry. Jim, you may begin whenever you are ready.
Thank you. Welcome, everybody. Welcome to Webinar Wednesday. Today we're going to talk about how to verify image quality using a ultrasound phantom. So with that in mind, let's get started. Verifying image quality is one of the most difficult things you can troubleshoot as far as ultrasound is concerned. It can be very subjective. The sonographer can use some very technical terms like mushy, grainy, and so when you're trying to get a feel for what they're describing, you really need to do a good interrogation, is what I call it, because unless you really understand what the problem they're describing is, it's very difficult to troubleshoot it. But once you get in front of the system and you bring your phantom, you can do many tests, which we'll talk about today, to help you confirm that there is a problem, or say, well, no, really it's imaging just the way you would expect it to do. And you should do these tests over time. As an example, when you perform a PM, you should take all these images and store them, print them out and store them with the system so that you can review them when you go back 6 months later, or when the sonographer calls and tells you that they feel like there's a degradation of image. So you can go back and say, no, it looks just like it did last time I was here. And at that point, maybe it's not an image quality problem, maybe it's a preset problem. So understanding whether the system's working the same as it was 6 months ago is an important tool. So what we want to do is start with understand principles of image quality. So we're going to talk about that. Understand the relationship between frequency and resolution. This is an important principle for ultrasound. Be familiar with different types of resolution, which we'll discuss. Understand the phantom and how it measures image quality. There's different ways of looking, different objects in the phantom to look at. And then we're going to finish with the different tests that you need to do while you're evaluating image quality on your system. So let's get started. What is image quality? Well, it's image quality problems, as I mentioned earlier, are amongst the most difficult to solve because they're truly subjective. Unless it's a dropout or something significant and you just walk in and you see it. But a lot of the image quality problems that you're going to hear about in the field is degradation over time. It didn't used to look like this. Well, now you're getting into the subjective area. Mushy, grainy, washed out, those are things you'll hear routinely. And it's really difficult to say, well, what does mushy mean? You know, what did it look like two weeks ago when you weren't complaining? And that's where you could really do yourself a favor by having images over time. And that's the next bullet. Has there been degradation over time? Well, the only way you're going to realize that is if you've taken the time to capture images when you get in front of the system. So every time you do a PM, again, what you're going to want to do is take your printouts and store them with the system or in a binder so that you have access to it, so that when you do get this call about image quality issue, you can simply compare apples to apples. What's it look like today versus what it looked like last time you did a PM? And the customer interview, I can't stress that enough. I've gone on to change from customer interview to customer interrogation, because I've come across problems where if I had just asked more questions and dug more information out of the customer, I could have solved the problem quickly. I had a call in Phoenix where they were having a color artifact problem, image problem, and it took me 5 days. I troubleshot it for 5 days and couldn't resolve the problem. I completely rebuilt the system from front end, back end, power, everything, and the artifact was still there. And the sonographer failed to mention that they had a third probe that was tucked away in a drawer that I didn't have access to, and when I plugged it in, the image artifact went away. So all along it was the fact that 2 probes had gone bad in the exact same way, and I was chasing my tail because I didn't do a proper interview or interrogation of the customer. So I can't stress that. Really get to know what the problem is. The following parameters influence image quality, and we have a list there: detail, spatial resolution, which is your ability to distinguish small structures, both axially and laterally, and we'll discuss that. You'll see that in a little bit. We'll define that a little more. Image uniformity, that you have comparable detail and contrast throughout the image. You don't want it dark in the middle and light at the top and bottom. You really want it to be a smooth image from top to bottom, left to right. You have temporal resolution or frame rate. This is the frame rate is affected by the number of focal zones, the areas you want to look at, and frequency of the probe. A fast frame rate, meaning that you have a good around 30 hertz, means that you're going to have a really smooth image, but it's not going to be pointed at specific areas. Whereas if you start pointing at more and more areas, say 3 or 4 spots on the screen, your frame rate's going to go way down. And the bad part of that is, yes, you're going to get a better image quality where you're looking at, but you're going to also lose frame rates, which could make it seem a little jumpy on the screen, kind of like the old movies, if you will. So frame rate's important to watch. Dynamic range, what's the largest and smallest signals that you can acquire and display. Spatial discrimination, its ability to limit artifacts and reflections from other locations. And then the bandwidth, which is basically the ability to reproduce signals appropriately. As I said earlier, we are going to define axial and lateral resolution. And if you can see the 2 blue dots in the image on the right, and then you have the gray kind of curved lines. Those lines aren't really there. It's just to illustrate that that's specifically where we're focused on, and that's why it gets narrow right where the 2 blue dots are. We're focusing, and specifically we have a narrow focus at that area. And if you're focused in that way, you'll be able to see both of the blue dots just like they're represented right there. If you were to lose focus in that area or be focused in a different area, those two blue dots would blur into one. They'd become one oblong object, so you wouldn't be able to tell that there were two distinct objects there. You'd only see them as one. And axial resolution means it's parallel to the beam path, which means top to bottom. And so axial, I always remember, is it's one object on top of another, top to bottom. Okay. Lateral resolution, on the other hand, is when they're side by side or left to right, and that's how I remember laterals, left to right. So you can clearly see here now we have three separate dots or groups of dots, and if it was in the near field at the top or the far field at the bottom, they would be seen as one object. They would blur into one. But where we're focused right in the middle, you can clearly see our focus is narrow enough so it only includes one dot, and therefore you could clearly distinguish that there would be two dots there. And that's an important concept that you really need to realize. If you see the phantom on the left, the image, you have what they call a resolution array. There's a circle around it. And this is where you can find out if your ultrasound system is giving you the best resolution. Now, we're going to talk about it a little bit more, but resolution's drastically affected by frequency. So keep that in mind too. If you're using a very low frequency probe, let's say 2 megahertz probe, your resolution is not going to be as clear as it would be if you're using a 12 megahertz probe. The higher frequency gives you better resolution. So make sure that you understand that concept, and it'll help you say, well, yeah, it's a little fuzzy, they may be blurred together a little bit, but it is a very low frequency probe, so we kind of expect that. And here's an example of that blurring together where the objects are individual dots, but you can see at the left-hand side that they're blurring into one larger object, and that would be poor resolution. In this case, it's obviously left to right, they're side by side, so this would be poor lateral resolution. Transverse resolution, to get your head around transverse resolution, you really have to understand that while you're imaging, a two-dimensional probe, a standard probe, is only a cross, it takes a cross cut, that's it. So you can't see front to back. You can see top to bottom, left to right, but you can't see front to back. And that's what transverse resolution is describing, is two objects front to back. And there's no way for us to see that. So transverse resolution does not exist or is not applicable when you're talking 2D. The only time it becomes applicable is if you're scanning in a 3D with a 3D probe, then it has the third dimension front to back, and you'll be able to measure transverse resolution. But in reality, the only thing you have is axial and lateral in a 2D image. Image uniformity, it's talking about comparable detail and contrast throughout the image. Well, it absolutely has to look the same from top to bottom. At some point, you're going to reach what we call the noise floor, which means it just can't penetrate any further and you're not going to get an image. So you want to adjust your depth such that you have the ability to see its deepest region, but you want to do so in a way that you can get all your detail and contrast for the image. If, for whatever reason, you have some kind of artifact that prevents you from seeing the contrast correctly from top to bottom or left to right, that's a problem with the system, and that's where you're going to have to start troubleshooting. And here's a picture of our baby. And I'd just like to point out, so I'm not sure if everybody here is familiar with ultrasound, but in this case, this is a 2D or grayscale image, also called B mode on some systems, which is basic imaging mode. But the objects that are displayed the whitest are the most dense materials, and the objects that are the darkest are your least dense, air, fluids. In this case, you can see towards the top of the image you have some clear, mostly white. That's your muscles, that's your abdominal muscles in this case. Then you can see the baby's forehead and jaw, obviously very dense bone. And in the middle you have the baby's brain. It's developing, lots of fluid, very soft tissue, so it's displayed a little darker. So, but clearly you can see that this image is uniform from top to bottom, even though there's different grayscales associated with the different densities. There's not a dark spot going through it. There's nothing non-uniform about this image. Contrast resolution. Not very many people really measure contrast resolution when they're doing their PMs, and I find that to be very disturbing. And why? Well, here you go. You have these 6 different objects starting at 15 decibels, and as you go down, finishing at minus 15 decibels. 0 decibels is the average tissue density in a human body. So 0 decibels would be right in the middle of all of that, between the 3 decibels and the negative 3 decibels, and that's measured at 1,540 meters per second. That's the standard or average velocity of sound waves in a human body. Well, in order to look at different densities of material, that's going to change your speed of sound. So at the top you have your very dense bone-like material at 15 decibels, and at the bottom you have your least dense, much like air, and so it's going to be displayed as dark. Well, if you were to be testing this during a preventative maintenance and you couldn't see one of those objects, let's say that you're scanning and you can see the 15, you can see the 6, but you can't see the 3 decibels, the plus 3 decibel. It's invisible. Well, that means that you have poor contrast resolution, and that's a real problem. The reason it's a problem is if you had a family member go in there and they had a cyst or a tumor that happened to be just at that 3 decibel range, the sonographer and the radiologist are going to miss it because you're not getting the kind of contrast resolution that the system's designed to give you. So you really need to perform a contrast resolution anytime you're doing a PM at a minimum. And if the sonographer is saying, well, I have poor image quality, absolutely this is a test that you need to go in and perform to make sure that you're seeing all 6 objects. And in reality, there's not only 6 objects you're seeing there, you're seeing a 7th object, and that's the average tissue. That's what all the white area outside of the circles, that's just human tissue. That's the average velocity of human tissue. So if at any point you miss one of these objects, it's because it's blending in with the background, and that's what you want to make sure that you don't see. And temporal resolution frame rate. It's a rate to acquire frames and display them. So when we build an image, we build an image 1 point at a time, and we do it depending on the frequency of the probe, 2 million times a second or 17 million times a second, and that's what affects your frame rate. That's one of the things that affects your frame rate. So you want to have a high enough frame rate so the image does not look choppy like those old black and white movies, but you also, the more frame or more focus points you put on there, what you're going to end up with is a better image where you're looking at. So it's a balance, if you will. Frequency will affect it, and focal zones will affect it. So as you increase the number of focal zones, you're going to paint a better picture in more areas of interest, but you're going to decrease your frame rate, and at some point you're going to decrease it to a point where the image will become choppy. So again, it's kind of a balancing act. And again, this would be an indication of how you could do an image, and you can see in the black and white image, just left of the baby's forehead is a little arrow-looking thing. That's a focal point, and that's a single focal zone. So what you're going to end up with is a much higher frame rate, but you're going to be focusing at that specific depth. So you can add to that if you wanted to see more areas of interest, but that's going to lower your frame rate. So it's a good thing to check your frame rate. If you're getting a choppy image, make sure that you don't have something going on that you're not expecting. And again, pretty average is 25 hertz, 30 hertz for a frame rate. Again, frequency of the probe will affect it, so there's no absolute answer to that. Dynamic range, largest and smallest signals acquired and displayed. Again, getting back to this picture, I kind of like to leave it simple, but what is the least dense material that you can represent on the monitor versus what is the most dense material? And you can see the grayscale bar on the left-hand side of the image, and really the darkest gray, not black, because if it was black, you wouldn't be able to see it on the grayscale because it would be blending in with the background. But the darkest gray that you can represent and the whitest white that you can represent is your dynamic range. So in this image, you can clearly see that you have a large variety of materials, fluid, muscle, and bone. Okay, we have some tests that we've been kind of gearing up towards, and we want to do these tests anytime we're doing a PM. So sensitivity, penetration testing, we'll talk about that. Axial and lateral resolution, we've talked about it, but we'll show you some of the tests on a Phantom. Contrast resolution, which is the 6 objects we talked about, being able to see that they're different densities and being able to clearly see them as different. Geometric accuracy, vertical and lateral. As it turns out, this is where you need to use your calipers. This used to be an optional test, for example, for American College of Radiology, but it's no longer optional. And again, it's very important that you're testing these, because your calculations that the sonographers use and the radiologists use are based on your accuracy of your calipers. So if you don't know that they're accurate, you could quite possibly be getting incorrect results or incorrect calculations. So let's talk about sensitivity and penetration testing. This should be done every time you do a PM on every probe that is associated with a system. Now, if you're in a department that say has 4 ultrasound systems and 20 probes, you don't need to do 20 probes on each ultrasound system. You can do 5 on one system, 5 on another. You just have to test each system and each probe to make sure it's performing the way it's designed. So it talks about penetration testing. It's also called sensitivity testing. It's the ability to display weak echoes from small objects. It's extremely important to get correct diagnosis, and we talked about that already, because all your calculations will be thrown off. Max depth is affected by output power, time gain control, compensation, gain, frequency, focus. You have to plan on all these. and optimize the system. It used to be that you had to do, according to American College of Radiology, ACR, that you only had to do the lowest frequency. They have made a recent change that you have to test the probe and the system on all available frequencies to get your max depth. Okay, so you want to record your findings on a hard copy. ACR mandates it has to be a hard copy, but even if it's not an ACR accredited system or department, you want to do these on hard copy, because when you go back to work on the system, you want to be able to have a hard copy that you can look at and compare that to what you're seeing now. And they should remain consistent over time. What we're looking at in all these tests, we're looking for degradation over time, and that's what we want to say. I absolutely see degradation, and now I have to get to the root cause. So all these tests, and you'll continue to hear this as we go through the different tests. So ACR says lowest frequency, or now all frequencies, and says that the depth is affected by output power. ACR then gives you very, very specific criteria as to how to set up a system, because you want to test the system apples to apples. If you say you have two people that work on ultrasound, and whoever, Joe goes in on January and does a PM, and then 6 months later Debbie goes in and follows up with a PM, but they're using two different presets and they're not comparing apples to apples. So you want to make sure that we completely set our systems up identical. And printouts is an easy way to find out how they did it in January, so that we can duplicate that in July when the 6-month PMs due again. So max depth, output power, they want you at 100% output power, time gain control so that you have a uniform image from top to bottom, gain appropriate so you're not blowing things up and making them blossom. The whites will be really blossom, so you have to adjust your gain. Frequency, again, you have to test them in all frequencies, and they only want you to have a single focal zone in the deepest region. And that kind of makes sense, because what we're testing for is max penetration. We don't want the best image from top to bottom. We want to see how far this probe can penetrate with these settings set up as described. So focus is a single focus point in the deepest region that you can see. All right. So if you do all those things, you'll be able to test all your probes and see what they're putting out as far as depth is concerned. 6 months from now, the probe was putting out and getting to 10 centimeters. You come back 6 months later and all you can get it to is 7.5. There's clearly degradation over time, and now's the time to find out what's going on with the system and be proactive about it. Axial and lateral resolution. Resolution is a minimum separation between two closely spaced objects which can be imaged separately. And I described this earlier a little bit, but here's the resolution array, and what you want to be able to do is scan that resolution array and see each individual point on that array or that resolution array. If you can't distinguish them, then you're going to have to start looking at why. Is it the frequency of the probe? Am I not focused in that area? If after all your efforts you still can't get every individual point visible, you have to make a call. Has it always been that way? Is it a problem with the probe because you're at 2 megahertz and it's just not designed to give you that degree of resolution? But you need to really understand ultrasound. Now, I said earlier, frequency is a huge thing to understand with ultrasound, because the lower the frequency, the lower the resolution, but the higher the penetration. So you're going to get very good penetration on a low frequency probe, but you're going to get very low resolution. So it's a trade-off. Whereas you get a high frequency probe, you're going to get great resolution, so you'll clearly be able to see the resolution array, but you have a hard time penetrating to it. They have a 17 megahertz probe that if you were to use it, you couldn't penetrate far enough to get to the resolution array. So there's you have to understand how ultrasound works in that regard. Low frequency, high penetration, low resolution. High frequency, high resolution, low penetration. So it's a trade-off. Axial is parallel to the beam, which means top to bottom. Lateral is perpendicular to the beam, which means the objects are side by side or left to right. Again, we can't do transverse resolution, so we don't list it here. If you were doing this on a 3D probe, you'd have to have a specific phantom to be able to run that test, because this phantom is a 2D phantom. It doesn't have 3D objects located in it. Speaking of that, there's many different types of phantoms that you can choose from, but we use the ATS phantom, the model 539 specifically, for all of our field service work. It's what we train with, and I love it. And I'm not trying to sell you on that particular product. I don't get any commission on that. I'm just, but it is a great product. It doesn't require any calibration. It's got a 10-year warranty. It's one of the less expensive ones on the market. I carried my Phantom with me for 8 years in my trunk of my car, never really taking it out except when I'm using it. I lived in Phoenix. It got 125 degrees, and I'd drive to Flagstaff where it was, and this thing looks brand new still to this day. It's just a very reliable Phantom. Some other ones out there, they have, instead of having a ballistic gel in them, they have liquid that evaporates over time. You have to have them recharged. You have to have them calibrated, and they're just a lot more work. This one requires no calibration. Again, 10-year warranty, and they're virtually indestructible unless you really try to hurt. Again, poor resolutions means two objects will appear as one. You want to take these hard copy printouts for every probe. You want to run this test. And again, like I said, findings should be consistent over time. What you're looking for when you're using a Phantom is degradation over time. Contrast resolution, again, we talked about it a little earlier, but this is a very, very important test. It's the ability to differentiate different tissue types without introducing noise. We clearly showed you the picture of the 6 round objects of different densities. You want to make sure you can see all those objects, and uses the amplitude of the received echoes mapped to a grayscale. That's the definition of 2D imaging. When I teach ultrasound basics, that's it. It's the amplitude of the echoes, okay, mapped to a grayscale. So the larger the echo, the more dense the object is. It's no different than being, if you have a concrete wall, you get a lot of echoes off of it, where if you have a soundproofed wall with foam and cones on it, you get very little echo. Well, that's what we're looking at here. We're just mapping it to a grayscale, where the darkest gray is the least dense and the whitest is the most dense. Again, can't tell you how important having printouts are. Print. I mean, if you end up at the end of a PM with 40 printouts, that's okay. That's a great visual representation of the image quality. So, and again, we're looking for degradation over time. The only way you're going to be able to do that is if you have consistent printouts. Geometric accuracy. Again, I mentioned that ACR used to call this optional. It's no longer optional. You must do it if you're ACR accredited, but I don't know why you wouldn't do it. The test takes less than 30 seconds to perform, and it verifies that your system's working and measuring correctly. You use the calipers to measure these targets, which are listed on the Phantom. They're actually defined on the ATS Model 539. It'll tell you two specific objects are 2 centimeters away. And so you make that measurement and you can compare what your ultrasound says to what the Phantom's calibrated for. And one thing to keep in mind, even though I said I kept my Phantom in the trunk of my car, weather, and it handled it, when you go to do a PM, if you had it in the car as an example, what you'd want to do is bring it in, do your PM. Don't do your measurements right away, your image quality measurements, because temperature does drastically alter the characteristics of the Phantom. So you want it to be at room temperature. So if it sits there for a half an hour while you're doing other portions of the test, it's great. Or if you've had it in your shop and it's already at room temperature, you're good to go. But it will have a significant impact on your measurements. And vertical distance errors are far less likely to occur than horizontal, so they're held to a higher standard. It's 1.5% of the measurement as opposed to 2% of the measurement for horizontal, according to ACR again. So what happens if you're doing a preventative maintenance and they don't meet that requirement of, say, 2%? They exceed that 2%. So what do you do then? That's a question I get often. Well, the problem with this is there's nothing you can do about it. In the old days, you had a little tweaker and you could go in and adjust the caliper distance to a calibrated Phantom, and you could make it read whatever you wanted it to read. That's a long, long time ago. Now, it's no longer that way. It's all software driven now. So really, if you fail a test and your only real recourse is to try reloading software, maybe the software got corrupted. So when you're doing this, be very consistent in how you take your measurements. Watch for degradation over time again. If 6 months ago it was right on 2 centimeters, say you're taking a 2 centimeter measurement, now you're failing, well, there's obviously degradation over time and you need to get to the bottom of it. In this case, I would definitely run a software reload if you have that ability. Now, some of the systems out there don't allow you to do software reloads without special access, such as Philips. You have to have a super user password, tech admin access. So how do we get around this? Well, if it truly is software, I recommend ghosting the hard drive. So you take a ghost to the hard drive, you come in and it fails this test, throw the old hard drive in that you ghosted because it was passing at that point, and test it. See if the caliper measurements come back into tolerance. So those are your options really as far as trying to correct this. But really, you really need to test this on every probe, even though the system should remain constant because it is software driven. But all your calculations are based on this. So if you're doing an OBGYN and you're measuring the head to see how far along the baby is, your calculations will be messed up if these aren't reading accurate. So keep that in mind. All right, that's what I have for Phantom testing. I sure would be ready to hear any questions you guys might have.
Hi Jim, this is Jamie, and we've had quite a few questions come in from the attendees, so I do want to dive right in with a number of them. We'll try to get through as many as possible, but attendees feel welcome to send your questions at your convenience using the questions feature. Any question we can't get to due to time limitations, we're going to send to Jim as well as the Conquest Imaging team, and they'll follow up with you offline. But Jim, the first question is going to be, for storage of images to CMMS databases, what to-dos do you suggest? i.e. printer, photo of screen?
Right. That's a great question. What we teach is, and what we do is we carry an analog black and white printer everywhere we go, and that meets the requirement of almost all ultrasound. There are some exceptions. The new Epic does not allow you to hook up an analog printer to it. The new Logic E9, Vivid E9 don't allow you to hit. You have to use a USB black and white printer. Not everybody wants to carry an analog printer and a USB printer. So what we do is we have to have a hard copy printout. So probably the next best thing is sending them to your DICOM server or your PAC system and having them print out from the workstation there and then storing them back at the machine. Pictures are not a bad thing. We all, most of us carry a smartphone now, and we can take a bunch of pictures. And the problem with that then is you're going to have to take them back to your workshop or wherever, transfer them to a computer so that you can print them out to get that hard copy again. So you really need to make sure that you have hard copies, and so there's some options for you.
All right, Jim, the next one is for clarification. You mentioned this earlier. What is TGC?
Okay, those are the sliders on the side of the, normally on one side of the control panel. There's 7, 8. There's variations in the number, but there's slide potentiometers that allow you to adjust the gain at a specific depth, as opposed to the gain knob adjust the gain of the overall image, where time gain controls, the sliders, the potentiometers, do it at a specific depth. So if you have a dark area in the image that you want to lighten up a little bit, but it's at a specific depth, you can use a slider to increase or decrease the gain.
All right, Jim, the next question is going to be, where do we find the ACR criteria for setting up US units for a PM?
Well, that's kind of a trick question. You can go to acr.org, www.acr.org, and they have it for all the imaging modalities, MRI, CT, and ultrasound. They do separate ultrasound versus breast ultrasound, so you have two different types. And they talk about criteria that they want you to test for, but they do not define anything to do with PMs, preventative maintenance. That is pretty much defined by the manufacturer. So to say what a PM requirement is for an ACR, you have to perform the PM in accordance with the OEM, the original equipment manufacturer. However, some of the tests that ACR dictates may not be part of that requirement, so you'll have to do those in addition to what the OEM says.
All right, Jim, and we have another question that's asking for clarification of something mentioned earlier. So in regards to the sensitivity penetration testing, this is a test that is set up to test individual probes per a consistent set of default settings. Is that correct?
Yes. To truly answer that question takes quite a long time, but basically you have to know what type of probe you're using. For example, if you're testing a linear probe, that's primarily for surface-oriented issues, thyroid, carotid vascular, small parts, breast imaging. So they're all surface-oriented studies. So when you take the time to set up for penetration testing for that particular type of probe, you want to use an appropriate factory preset. They don't want you using a custom preset that say the customer built themselves because they like those settings better. than the manufacturer. They want you to use the appropriate factory preset, and then all frequencies, and they want you to make output power 100%. So they're very specific how they want you to do it, and that's where you can get some differences in your reading. If you know, engineer A goes in and uses the wrong preset, he'll get one set of readings, and the next person comes in and says, well, this is supposed to be set up on this preset, and they get different results. And that can cause problems. That's why being very consistent on during PMs, keeping your preset the same, keeping your probes the same, and you should be then comparing apples to apples.
Great. And the next question, this has come in from a few attendees. Is there a particular type of phantom that you prefer that you use on a daily basis?
Yes, and I kind of mentioned that a little later in the presentation, but we use the ATS model 539. Again, the reason we use that one, there's others out there that you can find, but we find this one to be very durable. They're mostly affordable, about $2,500. But when you say that, some of the phantoms that I don't care for as much because they're liquid filled come in at more a higher cost than that. So when I say inexpensive, I don't mean to say that they're a couple $100, but there are more expensive phantoms than the ATS models. Highly recommend them. And if somebody is looking to purchase a phantom, I highly recommend have them come to us. You can go directly to ATS, but they'll charge you more than we will because we sell so many of them for ATS that they give us a little bit of a discount. So I think they're like $28.90 on the website of ATS, and we can get them to you for like $2,500. So we save a little money on that too. So.
Fantastic. That's great information. The next question is going to be, how do you perform probe leakage testing?
Okay, that's good. You have to have the appropriate safety analyzer. We are still using the Dell 601. We're investigating other newer models because they quit making the Dell 601. But it has to have the ability to test applied parts. And the Dell can do that. They can do ECG leads as well as probes, all in one analyzer, and that's hard to find. I don't like the automated testers because a lot of the automated testers will remove power when you're not expecting it, causing the system to crash. I can teach how to use the Dell 601 in a little under a minute, and you know, the automated ones can take you hours to program and really get comfortable using. So we use a Dell 601 that allows us to clip into a bath of water, and then we lift ground and we put the head of the probe in, not the whole head of the probe, but the lens, every bit of the lens is in the bath of water, and we take that measurement.
All right, the next question. My phantom had a note suggesting to store in an airtight container. Is this really advised?
Well, I don't know the model of phantom. I would guess that it's one of the fluid phantoms that I speak of, and they want you to keep the temperature pretty constant, you know, room temperature. And they want you to protect it from the elements because it does evaporate over time, and then you have to send them in and get them recharged, and they image just fine, but that's the limitation. The reason I don't like them is so not knowing the model of phantom they have, I can't really say, but I would guess that the reason they're saying that is it's one of the fluid filled ones, and they're trying to keep it safe from the elements.
Fair enough. Next question is, what are the benefits of low-frequency transducers?
High penetration. That's it. You have, we call them technically difficult patients, but let's say you have a very large patient and you're trying to do an abdominal study. You have to get penetration in order to see some objects, and so you're kind of forced into using a low-frequency probe. So you'll notice that a lot of the curved array probes are the 2 to 5 megahertz low frequency, because they are expecting to have to get to have that high degree of penetration.
What makes troubleshooting image quality issues difficult?
Well, that's a good question too. If it's an obvious image quality problem, meaning let's say they have a band going vertically through their image, it's completely missing information, well, that's pretty obvious as to see, well, yeah, there's something wrong. It's the image quality issues that aren't that obvious, the grainy ones, the mushy ones, the washed out ones, because, you know, we're not sonographers, we aren't seeing what they are seeing, and we didn't see what the image looked like a month ago when they weren't telling us there's a problem. So we have nothing to compare to. So that's why having a good customer interview and maybe an old study, maybe they can go back and show you a similar study that occurred a month ago and say, see, this is what it used to look like. But if you can't get that real good feel for what they're trying to describe, you don't know what you're troubleshooting. So it makes it real difficult. That's where the customer interrogation and old images will really help.
Can you repeat what you said regarding testing every probe on every system?
Okay, I said you don't have to test every probe on every system. You have to test every probe, but you don't. If your department, for example, the ultrasound department in the hospital has 4 ultrasounds, but they have 20 probes. You only have to test all 20 probes, and you have to test all 4 systems, but you don't have to test 20 probes on each of the 4 systems. You can do 5 on one, 5 on another, and so on. As long as they're all being tested for image and electrical safety, and you're testing each one of the systems, then you're in compliance with any accreditation program out there.
From which side, scan plane in parentheses, on the Phantom do you do each of these QA checks with?
Okay, I think I understand what he's asking. You may have to vary on the ATS. The beautiful thing about the ATS again, 539, is you can rotate top. It's a 4-sided Phantom, so you can use any side you want. And the reason that's nice is if you're getting, I mentioned earlier, a high-frequency probe will have poor penetration. Well, you may have to rotate the Phantom in this case in order to get the penetration that you need to see the object you're looking for. So we normally keep it just upright for most of our tests, but contrast imaging is an example where when I get to contrast imaging, I rotate the Phantom so that the objects are now across the top, and virtually any probe out there will be able to penetrate enough to see those objects, so that you can do contrast verification without a problem. So if that's, I think that's what they're asking, is on an ATS, which side in particular do I use? We normally set it straight up, but there are instances where you'll want to rotate the Phantom to get the best readings.
All right, we're going to see how many additional questions we can get through. Is there factory presets for individual probes, and if so, where do you get those?
Well, each OEM's a little different, but almost all of them refer to them as presets, as you know, as stated. And the modern systems, it's kind of a trick question. The modern systems normally, as an example, the E9s, the Epic, they will not let you select a preset that is not associated with that type of probe or that probe. So they keep you from getting in trouble. The old systems weren't like that. The old Logic 9, as an example, you could pick any probe and any preset, and you could mess it up real easy. But anymore, the newer systems, they lock you into a type of preset for that particular probe.
All right, Jim, I do have quite a few questions that are still in queue. So attendees that have submitted a question, and unfortunately we are right at the 60-minute limitation for Webinar Wednesday today, I'm going to go ahead and send all these questions over to Jim and the Conquest team. I know they're going to follow up with you promptly offline to get the answers that you need. Again, Jim, thank you so much. Great job today on the webinar, and we certainly appreciate you sharing your time and knowledge with the attendees that were online. Thank you specifically to Conquest Imaging. We appreciate your support in our webinar series. One lucky attendee will win an Amazon gift card for completing the post-webinar survey, which is going to appear shortly on your screen. You must complete the survey to obtain the certificate of attendance. If you do not see the survey, email us at webinar@mdpublishing.com. An updated list of webinars that are coming you can find on technation.com/webinars. Look forward to seeing everyone next week.